Hi everybody, welcome to this video and this lesson. It's a class actually. I'm going to go into quantitative aptitude. A lot of you have been requesting me to solve some questions on QA for you people. So I'm going to start this series for all of you. You will have to provide me the questions. Of course, I can bring questions from my own also, but I would love it if some of the YouTube viewers bring up the questions for me. And I pick those questions, good quality questions, which will help all of you preparing for any aptitude exam, be it CAT or placements or even other aptitude exams like IPMAT, CLAT or banking and SSC exams, etc. So this QA series is meant to help all of you, and this is a series of must-know questions that I'm doing. So and this will of course be part of my my classes series that I am also doing on YouTube. So I'm not doing this one live. I'm just doing this as a recording. And the questions, this must-know questions that we are picking up today, have been sent to me by Gublu on the YouTube channel, and all three. Thank you so much for those questions, Gublu. I'm quite sure that's not your real name, but that's the name that appeared on the chats on the comments. So I'm picking these questions. They're good quality questions, and I would love to solve them for you and show you how to do them. These are all from number systems. So here goes. Without any further ado, this is the first question. So the question says the HCF of 9,000 and x is 60, where x is the natural number less than 9,000. Find the number of possible values of x. Right. So this and the options are 24, 30, 40, and 36. So the options don't help you in this question much. This question is based more on more of the understanding of the structure and the situation that is being dealt with. And the first thing you need to understand in this question is that when you tell me when you say that, let's say there are two numbers whose HCF is, let's say 5. So the two numbers would necessarily be in the form of multiples of 5, first of all. So the two numbers can be thought of as 5a and 5b. And even there, between 5a and 5b, between a and b, you will see that the relationship between a and b is that they should be co-prime. The reason for that is if you do not take a and b co-prime, the HCF will change from 5. The logic is, the logic can be seen very clearly if I say I take A as 2 and B as 6. So if A is 2, then 5A becomes 10 and B becomes 6, 5B becomes 30. So the HCF of, because 2 is a common factor for both these, for A and B in this case, the HCF itself is getting multiplied by 2 and becoming 10 in this case. The HCF no longer remains 5. So the condition for 5 to remain the HCF, if I am taking two numbers 5A and 5B, the condition for 5 to remain the HCF is that A and B should have an HCF of 1, or they should be co-prime numbers. And this applies to 3 numbers also. But in this question, this question is going only up to 2 numbers. So let's have a look at what this will do for us. So the question says the HCF of 9,000 and x is 60, where x is the natural numbers less than 9,000. So if I think about this question, the way I can think about it is, the way I can think about this, let me take a blank slide, is that if my first number is 60a, my second number is 60b. Now in this question, the first number is already given to me as 9,000. So the value of A is kind of fixed. And for the second number, we are told that the second number is less than 9,000. This was the second piece of information given to us. You can check that there. X is a natural number less than 9,000, right? So in this context, your first reaction has to be that the value of A being, if the value of 60A being 9,000, it basically means that the value of A is 150. And given the fact that this is 150, it means that the value of A is 2 into 3 into 5 into 5. Now, when you're looking for two co-prime numbers, one logic that applies there is that when you want a number which is co-prime to this number, you have to build a second number using prime numbers. You can use multiple prime numbers, or you can use a single prime number. You can use powers of multiple prime numbers. You can use P1 into P2. You can use P1 square. You can use a single prime number P1. But what has to happen is that in the prime factors of this number, if this is A and B, I want B to be co-prime, then the prime factors of B, there should be no uh, 2 or 3 or 5 in this case. Because if there's a 2, 3 or 5, then they don't have an HCF of 1. Co-prime numbers mean an HCF of 1. Two numbers co-prime means an HCF of 1. So we can start thinking about, okay, if I look at this number, then first of all, because 60B is less than 9,000, this value of B has to be below 150. So the question now mutates to finding the number of numbers below 150, which are co-prime to 150. That means they don't have 2, 3, 5, any 2, 3 or 5 in them, in the prime factors. So the first number that you should visualize here obviously is B. B can be 1. Because if I take B as 1, it's very evident that this number becomes 60 and this is anyway 9,000. So the HCF will become 1. And then you start thinking, okay, the other structure is one prime number. The other structure is one prime number. How many single prime numbers do you have below 149 becomes the next case. And for that, you should know, and this is something which I've given in my quants book also, that there are 25 prime numbers below 100. There are 25 prime numbers below 100, out of which 2, 3, and 5 are the first 3. But you cannot take, when you think about B being a number of the form single prime number, only P1. So in that case, you cannot take 2, 3, 5 there. See, where I'm heading to is this, that I can visualize that B, the value of B can be a single prime number. It can be a product of 2 prime numbers, or it can be a product of 3 prime numbers, or it could be powers of a single prime number, something like this. And I can rule this out because given the fact that I cannot use 2, 3, or 5, the minimum triple prime number multiple is 7 into 11 into 13. And since there's a constraint in the question that B value has to be below 150, we cannot use a triple prime number structure. So can we use a P1 square, P1 square into P2? Obviously, P1 cube will also not work. You can have, I mean, by default, you can have powers of P1, but given the fact that this is less than 150, and you cannot use 2, 3, 5, 2, 3, and 5 are not available for you. You cannot use a 7 cube, for example, because 7 cube is 343. It's above 150. So can you think of structures where there's a P1 square into P2? And once we get into that, we'll see whether we are missing any structures in the counting. So when you start thinking about the structure of B being only P1, that means only one prime number. So there are 25 prime numbers below 100, out of which 3 is not counted. So there are 22 of them. And then from 100 to 150, I don't expect that you will remember those prime numbers, kitne hain, but you can quickly find them out. 101, 103, 105 is not prime, 107 is prime, 109 is prime, 111 is not prime, 113 is prime, 15, 17, 19 is not prime. What else? 121 is not prime, 123, 25, 127 is prime, 127 is prime. Yeah, it's not divisible by 3, not divisible by 5, 7, 11. Yeah, so that's 3, 6. And then you also have 129 is prime. No, 129 is a multiple of 3. 131 is a prime number. Then you have what? 131, then 139 is a prime number again. And 141, 143, 145, 147 are not prime, 149 is a prime number. So let me just check this. 131 is prime, 133, 135, 137 is not. 133 is multiple of 7. 135, of course, not prime. 137, 139, 137 किससे multiple है? 3 से नहीं है, 7 से नहीं है. 11 से नहीं है. So 137 भी prime है. 137, 139, 149. So 3, 6, 10. So that makes it 33 total of the form P1. Then you have to try to think of the form P1 into P2. Two prime numbers which are not 3, 5, 2, 3, 5. And then two prime numbers which are not of the form 2, 3, 5 and have a value less than 150. So you start thinking about that. The first value that comes to mind is 7 multiples of 7, 7 into 11, 7 into 13, 7 into 17, 7 into 19. That's 133. And then you have 7 into, the next one is 7 into 23, which is crossing 150. So that makes it 4. And then you also have using of 7 as a square. You can use 7 square, 49, 11 square, 121. And so squares में 13 square is not possible because above 150. And then when you go to 50, when you go to a number like this, it's not possible because the lowest value is 7 square into 11, which will be above 150. So the last value that you have here is what? So there are 4 plus 2, 6. And there's another value where you can use another structure like this, which is 11 into 13. The next two prime numbers, lowest prime number is 13 into 17, which is crossing to 150. So you have 7 such situations here where you are combining two prime numbers or squaring a prime number to get a number less than 150 and co-prime to 150. So the total number of numbers that you're getting here is 33 of a single prime number form, including the number 1, right? So as a single prime number form 22 plus 10 are, so that makes it 32. But the single prime number, single number 1 is also part of it. Don't forget that. A lot of people miss this out. And then you have these 7 cases. So the correct answer, based on this reaction, the correct answer to this question is 40. Now let's have a look at the second one. Let's have a look at the second question now. Find the greatest number of 4 digits, which when divided by 10, 11, 15, and 22, leaves remainder of 3, 4, 8, and 15 respectively. So in this question, the basic logic is that a remainder of 3 when divided by 10 means a 10n minus 7. It means the number is of the form 10n minus 7. 10n plus 3 also means 10n minus 7. When divided by 11, if the remainder is 4, it means we have a number of the form 11n plus 4, which is also a multiple of 11 minus 4. Likewise, the number we are looking for is also a multiple of 15 minus 7, because it's giving a plus 8 remainder. And when you divide by 22, it's giving a remainder of 15, which means the number is 22n plus 15, which also means it's 22n minus 7. So these are the 4 numbers, or these are the 4 kinds of numbers you're looking for. So you're looking at one number which has got all these 4 properties. That means it should be 10n minus 7. It should be 11 minus 4. It should be 15n minus 7. And it should also be 22n minus 7. ये चारों होना चाहिए इसमें. ये 10 and minus 7 भी होना चाहिए, 15 and minus 7 भी होना चाहिए, 11 and minus 7 भी होना चाहिए, 4 क्यों लिखा है मैंने? It should be 11 and minus 7 also, and it should also be 22 and minus 7, which means that we have to find this number, we have to look at a common multiple of 10, 11, 22, and 15. We have to look at a common multiple of 10, 11, 22, and 15 and subtract 7 from them. And the question being asked is greatest number of 4 digits. So this property that we are looking for, the property explained in the question will be for any common multiple of these 4 numbers minus 7. So we first find out the LCM of these 4 numbers. So the LCM of 22, 11, 15, and 10 is 22 into 15. That's it, 330. And if 330 is the LCM of 22 and 15, the largest common multiple of 22 and 15 in 4 digits, you can visualize as 9,900. So this is a number, any number, I mean 330, 660, 990, these will all be common multiples of 330 of these 4 numbers, 10, 11, 22, and 15. Let me just check whether I've got this right. 22 and 15 are co-prime, so I can just multiply them. 11 is already part of 22, and 10 mein 5 and 2 hai, which is part of 5, 15, and 20. Yeah. So effectively what you need to understand here is that if you do minus 7 on any of these, 990 minus 7, that's 983, 660 minus 7, that's 653. It'll have the property that if you divide by 10, it'll leave a remainder 3. If you divide by 11, it'll leave a remainder 4. If you divide by 15, it'll leave a remainder 8. ये property सब में रहेगा. ये चारों property, all these numbers will have. But we are looking for the largest 4-digit number, greatest number of 4 digits. That's another part of this question. So the correct answer will be 9,900 minus 7, which is 9,893. Because the next multiple of 330 is going to cross 10,000, which is going to be 5 digits. So 9,893 is the correct answer to this question. Right? It's none of these here. And the last question, third question for today, which was also sent by Gublu. N is the smallest positive integer such that n by 2 is a perfect square. Now, before you go ahead in this question, understand what this means. If n by 2 needs to be a perfect square, it means, and this is all from the vision of prime factors that you get this. If you have a number n divided by 2, and this has to be a perfect square, it basically means that in the prime factors of n, the number 2, the prime number 2, has to have an odd power. The logic is that for a number to be a perfect square, all its prime factors should have even power. This is the basic logic of a prime number, of a perfect square. All the prime factors should have an even power. So if you have a number like, for example, 2 raised to 4 into 3 raised to 8 into 5 raised to 12, this is a perfect square because if you take the square root, you will get half of this, and half of this, and no under root signs in the value of the answer. Right? The moment this is 2 raised to or 3 raised to 9, if one of these powers is odd, then this number is no longer a perfect square. So this is one of the properties of a perfect square. So in this present question, we are told that if I divide n by 2, then I get a perfect square. This means that the existing power of 2 inside the prime number, inside the number we are talking about, has to be odd, which means it has to be 2n plus 1. It has to be a multiple of 2 plus 1. It has to be an odd power because only then when I divide it by 2, will the number become a perfect square. Right? So this is my first condition. The second condition in this problem is that when divided by 3, it becomes a perfect cube. And the third condition is when divided by 5, it becomes a perfect fifth power. So again, for a number to be a power of 3, a perfect cube, for a number to be a perfect cube, what should happen is each of the prime numbers of the number, each of the prime factors of the number should have a multiple of 3 in its powers. So for example, every perfect cube will look something like this. 2 raised to 6 into 3 raised to 3 into 5 raised to 12 into 11 raised to 3. I mean, the moment you have one of them as 4, one of these powers is 4, then this is no longer a perfect cube. Right? So now in the present question, we are told that if n is divided by 3, we get a perfect cube. This means two things. This means two things at this point. The first thing it means is that this number that we have, the number we are trying to trace, n, has to have 3 as a component in its prime factors. And also the power of 3 has to be 3n plus 1, because when I divide it by 3, then this plus 1 will get deleted and I'll get a value of 3n. At the same time, this is also telling me one more thing. It is telling me actually two more things. One, first of all, this number when divided by 2 should become a perfect square. So we got this condition based on that. But it adds an additional condition to this number. And that is because when you divide by 2, only this power will get affected. So after division by 2, I should have 2 raised to even power into 3 raised to even power. Which means that this 3n plus 1 we are talking about cannot be just any 3n plus 1. It has an additional condition that it has to be even. Only then when you divide by 2 will the outcome be a perfect square. And likewise, when you divide this by this number by 3, you divide this number by 3, it should be a perfect cube. Now we have already taken care of this condition that 3n plus 1 agar hai iska power, to divide by 3 mein perfect cube aa jayega. But that then tells me that the power here has to be a multiple of 3. It has to be a multiple of 3. Not only this power has to be 2n plus 1, it also has to be a multiple of 3. Let me explain this through a different example. Suppose I disobey this condition and I use 2n plus 1 only. So I said 2 raised to 5 into 3 raised to 4. So if I divide this number by 3, I'll get 2 raised to 5 into 3 raised to 3. Now this is not a perfect square because this number is not a multiple of 3. So this number is necessarily not just 2n plus 1, it has to be a multiple of 3 to meet this condition. And the same thing is applied one more time when I'm told that, in this question, when I'm told that n divided by 5 gives me a perfect fifth power. So it tells me that two things, that there has to be a 5 component with a power 5n plus 1. Right? And based on the first two conditions, this power also has to be a multiple of 2. And this power also has to be a multiple of 3. Right? Because the condition that was on the power of 2 to be a multiple of 3 will also apply to the power of 5. And the other factor that you should understand here is that, when you talk about 3 raised to 3n plus 1 being even, now I have to apply the other two conditions to this. One is that this is even, right? The other condition is that this should be a multiple of 5 also. And the third condition on power of 2 also is it should be a multiple of 5. So there are 3 conditions on every number. On the power of 2, it has to be 2n plus 1, a multiple of 3, and a multiple of 5. You should be able to visualize 2 raised to 15 for that, the smallest. And And the question is then taking us to this condition that we are looking for the minimum sum of a plus b plus c, right? And n is also defined as the smallest positive integer with this property. So there will be hundreds of millions, in fact, not millions, there will be infinite number of numbers with this property that you divide by 2, it becomes a perfect square, divide by 3, becomes a perfect cube. But the question is talking about the smallest such number. So that's why we are trying to go for the least values here. So 2 raised to 15 fills all these conditions for power of 2. It's a 2n plus 1 number, it's a multiple of 3, and it's a multiple of 5. Likewise, 3 raised to 6. No, I want 3n plus 1, right? So 3 raised to 10. I want it even and multiple of 5. So 3 raised to 10 fills all these 3 conditions. It's a 3n plus 1 power, it's an even number, and it's also a multiple of 5. And 5n plus 1, multiple of 2 and multiple of 3, it's easy to spot, 5 raised to 6. So this is the number. You can check this. If I divide by 2, the number becomes 2 raised to 14 into 3 raised to 10 into 5 raised to 6. If I divide this by 3, on the other hand, if I divide this by 3 on the other hand, this number becomes, if I divide this by 3, this number becomes 2 raised to 15 into 3 raised to 9 into 5 raised to 6, which is a perfect cube, definitely, because all the powers are multiple of 3. And if I divide this number by 5, if I divide this number by 5, I have 2 raised to 15 into 3 raised to 10 into 5 raised to 5, which is a perfect power of perfect fifth power. So essentially, you realize that the sum of ABC, the powers of the prime numbers, is that's what the question is asking me. If I go back to the question, can you see what it's asking you? Find the minimum sum of ABC where A, B, and C are the powers of PQR, where PQ are the prime numbers, distinct prime numbers. So 31 is the correct answer, 15 plus 10 plus 6. That's the correct answer. So I hope you enjoyed this session, and do let me know if you want more of this. We are just trying to revamp our YouTube channel and make sure that it gets more in sync with what our audience wants. And I hope you enjoyed this, and do like the video, do comment on the video. Those of you looking for more questions and solutions from my side, please start posting those questions on the comments. I'll try to do as much as I can. And of course, do follow the YouTube channel, and do like and subscribe it. Thank you so much. Bye-bye.